Okay, thank you, Yoko, for the introduction. Hello, everyone. I hope everyone is well. Can you guys all see my screen properly?
Yes.
Oh, good. Okay.
Yes.
Um, okay, then let's get started. So before we get into the detail, I want to just mention that everything is all the files, presentation, and plugins we are going to use today are all in the Google Drive. So if you haven't got the link for that, maybe Yoko can help share the link in the chat for people.
Sure.
Okay. So before we start the actual content, I'm gonna do a quick introduction about myself. Um, Again, my name is Ping-Hsiang Chen, and I'm a British architect and working as a computational designer in an architecture firm called KBF. I'm working in specifically in an applied research team focusing on computational strategy and implementation in the architecture process. And I'm also the computational design course tutor at University College of London at the Bartlett School of Architecture. And I also co-found computational education platform called DSAP with Doreen Beneath and Akshay Goya. So we try to promote computational design. So as the image suggests at the right, that probably give you a sense of what kind of works that I've been doing. And pretty much they fall into these three categories: geometric system, robotic construction, and platform-based automation. So if you're interested in those works, I think one place you can probably check out more details is Mamomani Architects, the website, which is the firm that I used to work for about almost 4 years. So if you're interested in that, and then we can have a separate discussion in the end of the session. So let's just get started. Today's session, it's not gonna be too hard in terms of programming concept, I will say. I will focus more on how we can sort of do a bit more sort of a design application. Okay, so talking about the title, function composability, I would like to address this word called composability first. It's a term that used in computer science as a sort of design, system design principle that deal with the interrelationship of elements. And essentially that deal with a complex sort of function that has a tight relationship with different elements. So when one sub-function behavior change, the overall outcome will be different. And I find this idea is extremely interesting because that sort of resonate to the way how we approach design and modeling position. So the image below suggests that complex cathedral floor plan is composed by series of primitive geometry like a triangle, circle, and through this accumulative process that you get the overall complex outcome. So in this session, the emphasis will be placed on how geometric function in Grasshopper specifically can be composed. And talking about composability, another things that we will also touch on is interchangeability from one function to another, which is in the sort of programming term a little bit difficult to do, but in Grasshopper C#, there is a way to sort of quickly assemble things together without thinking too much. So we're gonna look at that. And as a result of the session, we will be investigating how to create a shape grammar based on the principle introduced as a final sort of exercise. Okay, so the topic itself can be further broken down into 4 parts. In the beginning, we're gonna talk a little bit about general concept of Rhino common, how to deal with different data type, all these kind of things. And then we will be looking into a specific function in Rhino common called no-encode and its use cases. And then we will sort of pull ourselves out from the script environment to talk a little bit about Grasshopper data structure, which is probably a very important part in dealing with parametric modeling in Grasshopper. And then the last part will be the geometric composition exercise, which link to the following subtopics that we will just briefly touch. One is emergent behavior. So as opposed to sort of top-down approach, we're gonna talk about this bottom-up approach, and then we will also talk about L system and the shape grammar. Okay, so to begin with, I would like to do an overview on how we normally do basically a design in Grasshopper. So Grasshopper it's a program that is essentially very good at doing function composition already, as opposed to the traditional modeling procedure where we always deal with one object at a time. And with this approach, you are able to basically compose different part of your design and work together as a whole. So for instance, the image at the top is a house that can be broken down into 4 parts. But for me, what is even more interesting if we can sort of take those A, B, C, D part into a separate part and start swapping them, right? I mean, not probably we won't be able to make a functional house, but then it has a lot of like imagination and creativity to look at the how we normally approach objects. So the image at the bottom is a work sample from one of my students, a group of my students from the Bartlett School of Architecture. Okay, so let's talk a little bit about how we normally what kind of function composition method that we normally employ in our design process in Grasshopper. So I think the most basic one will be simply just assemble components together, like the image here. And it's really good to kind of do something that beyond how we normally do object modeling, right? So in Rhino, you can do one object at a time following the function, but you won't be able to do something more than that until you do this kind of step-by-step approach. However, if you continue doing this, then you probably end up with kind of a continuous linear kind of a script where everything sort of tangle together. Which is a little bit hard if you want to do something like what I suggested earlier, to do sort of interchange between one part and another. This is where another approach comes in, which called cluster. You can start clustering stuff together to become a function that has much more, or with an emphasis on usability. And with this approach, when you change the elements inside a cluster, the same cluster inside the Grasshopper definition will also change. And then, so we were gonna, I'm gonna talk a little bit about the cluster and the Rhino common method in detail a bit from the application side. So for Rhino common, it's probably quite identical to the Grasshopper components too. It's just the way how we sort of assemble is slightly different just from the infrastructure point of view. However, script component is extremely good not only to assemble the Rhino and Grasshopper function together. It also allows you to do things such as assessing the functionality from Grasshopper and Rhino document to do some automatic work, as well as extending the function available in this program, right? However, if we try to look at this point, try to compare with these two, cluster is very good at assessing additional functionality from third-party plugin. Versus if we look at the Rhino script, the scripting component, you have to implement everything from scratch. That make the design process very difficult. If you know that there is a component available, there's a function available you need to use, but you want to work with this, the idea of maybe iteration or complex calculation, then you have to implement that from scratch. And even you are able, to do that, to deal with all sort of infrastructure challenge by doing all this assembly namespace, and it's quite likely you get into the level where you have to dig into a source code if the documentation is not very clear, right? You have to understand how the person who wrote the code structure the script, and then try to kind of look at this interoperability between the different programs. So it's kind of difficult. So this session is really to sort of focus on how do we do things in sort of in between the behavior of cluster and Rhino comment here. Okay, so take another look from the operational side, from the cluster and Rhino comment. So what's the difference between these two? So in a way, the components in Grasshopper also represent the function in the Rhino Command API. So what's the difference? So one thing that you will probably notice the most is you don't actually need to handle too much about the data type. So in Grasshopper environment, for instance, let me just put this out. At the moment, just you don't need to do anything. So for instance, we have 3 different type of curve. In Grasshopper, there's no difference, right? You can, if you want to get a center point, then you just simply get a center point from all of them. But from the script point of view, they are actually different. So if we look at the, I hope that you guys can see my screen in Visual Studio clearly. So I'm gonna do a quick demonstration. So from the script point of view, they are actually different in terms of the method attached to a specific type of geometry. So let's look at circle first. So if we want to get a center point, then we can use a method called center. Here, called center, and it's a property. So for instance, like this, then we get a point here, which is identical to the point we get from Grasshopper. And then if we try to look at the curve, you will notice that curve doesn't have the function or the property called center. Then this is where you have to find an additional method to get the point, right? This is where we have to introduce something called mass area mass property, and then that's called area, and then area mass property, the compute, and then we put the curve in, then we can get the centroid from the curve, right? So we get the point, and now if we look at the polyline, then it's even more different. If we do the same thing, first of all, we start with getting the center as a start to test, poly, the center. You find out actually this method, this geometry, polyline, has a function called center point. So, and this is different from the center from the circle, because this is a property, it's a method. So you have to do it slightly differently in order to get the center point. And if you check this against to the area in a component in Grasshopper, you will notice that the center point is not at the right place. And then you will wonder why they are so different. And then even you try to do it with this method, we call it area 2, and we do poly here. You will find out then it gives you this complaint, right? This complaint error. That is because it doesn't take the type polyline, and this is where you have to convert the geometry into different type. Whoops. Let me just drag this a little bit. You have to convert, and then you can get the area, and centroid. Right? So just to do a simple task, then you have to really understand the difference between all different type of geometry and method. So this sort of create a barrier for people to do this kind of interchangeability, because one thing that Grasshopper component is really good at is it has sort of a luxury having a lot of sort of things that implement on top of the basic functions. So Grasshopper itself do this kind of conversion for you. As well as you notice that when you deal with Grasshopper components, sometimes you need to fit, you give one probably one input or two input, three input, and they still work. But in the scripting environment, this become really difficult, right? So this is where why when we do function composition, that become a little bit difficult, because you have to create a lot of if else. If you find is this type of geometry, then you implement this method to do conversion. Okay, but however, script environment is really good at doing this kind of crazy calculation, right? It can quickly iterate through, where if you do it with this cluster logic, you won't be able to do that. So this is what I want to introduce. This spatial function is a really weird function called no-encode in Rhino common environment. It's not a really new function. It was created back in 2013, but if you go to Rhino forum to kind of search different discussion, you will find that the volume is still really low. It's about like 30, maybe it increased a little bit to 40, but it's still really few. And I think there are a few reasons that is not very interesting for people, or why people are not using it, but I will sort of address that and then talk about the useful cases that you can use it. So what is no-encode essentially? No-encode is a function that allows you to call Grasshopper component as a call block. So it's quite similar to how we deal with Grasshopper components in Grasshopper canvas, where you only need to handle input and output. So the data type is handled by the Grasshopper component itself, as well as the data structure. When you deal with scripting environment, then you have to constantly create a lot of storage. It depends on the type of data you get, right? You have to do list, you have to do data tree, all these kind of things. But with just native Grasshopper component, you basically just need to chain up all different type of components that you want to form a certain function, and then it just works fine. Unless you have to do some complex data matching exercise. Okay, so we're gonna see how we can use this function to do something like this. So just have a quick look of this geometry. You can probably think about how to create this in Grasshopper, right? You have a cube and you do Voronoi, and then you probably try to mesh it, and then you join them together to form a continuous mesh. But to implement something like a Voronoi, if you go on Rhino Common API or Grasshopper SDK, you probably don't find this function because it's not really documented. That makes the process very difficult. Okay, so we will be looking at how to do this in probably 5 minutes. Okay, so first of all, now let's get into Grasshopper, Grasshopper and C#. Let's get our hands on the script. I would like to sort of do sort of a warm up to do things in a traditional way, and then later we can look at how to use the no-encode function to do the same thing. Okay, so let's do this. Okay, and you guys all have the file here, right? So these are the file I prepare for you to use, so that you don't have to, you know, some typing for, you know, just to speed up the process. So the first one we will be looking at. Let me just disable this. We're gonna look at how to do this very basic things first. Okay, create a circle and divide a circle into points. Let me just do this now. I need to do this. Wait a second. Just give me 2 minutes. Okay, let me just say print hello. Oops. Make sure it works. Okay, it works now. Okay, we can stop. Okay, so if we want to do the same thing in script environment, there are a few ways to do, right? So let's say we create a circle first, circle, call C, and new circle, and then we get the center point. We get a point called origin, and then give a radius 10. Right? This is how we normally create a circle. So now we can put a circle in Grasshopper. Let me just hide this. Right, so now we have a circle here, and if we want to get point, there are a few options. So what I want to look at is to look at the option to use a t-value. I guess that is also one of the most common options in Grasshopper. So we have the number of division that we want, and we can specify a t-value. Let's say 1.0 divided by none, and then let's have a look. First of all, let's create a loop and say we want to run through 10 times. So we have a slider here, say we are going to run through it 10 times. So first of all, before run through all the t values, I want to look at just one number. So I'm gonna start with circle and get point, use the point at method. And you will notice one very interesting things from here. I'm gonna output a circle too. Okay, so here I will have a circle with a point. Okay, so if you try to get a point here, okay, with this point on curve method, you will notice that the point is not at the same location. Right? And the reason being is because we have to actually reparameterize the curve in order to get the domain, and then we can specify accordingly in relation to the curve, right? So to do that, we have to convert this circle into different type of geometry, because at the moment circle doesn't have the function to get domain. So we have to do maybe, let's say, R curve C, AC equal new R curve, and then put C inside. So now we can find we can define the domain between 0 and 1. Okay, so now if we do this again here, okay, wait a second, this should be AC, and then the points are at the point is at the right location. So this is where we can start doing some interesting things. We can put t value in m times I, but after we do that, we have to put the points in somewhere. This is where we have to create sort of a placeholder, right? So we have to create list of points, oops, these points, call points, new list points. So now we can add those points. Let's call this just a temp point, maybe TP. Okay, we have points, and then we can add those points into TP in there. And then we can basically print A. I'm going to do here, 8 PTS. Now we get a bunch of points. So just to get a bunch of points, then we have to go through this. What about if we're gonna do it again? So we're gonna put this, the circles on top of points, and then we're gonna divide this again, okay? So this is where the complexity comes. So let's do that. To put a circle on top of this point, it's not a problem, because we can simply just do create a new circle called new circle. And then we do new circle, and then TP, and then we maybe give a smaller radius, say 3. Now we have a circle, and then we can divide the circle into points. So this time I'm gonna look at a different method. If you want to use the same method, you basically implement everything again here. I'm gonna look at divide curve method. So we have NC. If we want to divide curve, we first of all need to convert to the right type that has the function, right? That has a function. So we convert into 2 NURB curve, and then we do divide by count. And divide by count, this method require number. That's use the same number as what we have here. And then we say include the last point following the hint here. And then we say we need to output points. So then this, because of this keyword, we have to create a temporary storage for those points. Say output maybe 10 points. So we do it here. Wait a second. Let me just put it here. We say points, and then TPS. So we put points there. Okay. And then lastly, then we have all the points extracted from the circle, the subcircles we create, then we have to output those points. So this is where we have to even create a more complex sort of storage to store it, because we know that we have a list, and then if we try to divide it again, it's gonna be a data tree. So this is where we do data tree, and then points, 3D, and then we say final points, maybe final points, data tree. Okay, so to put things into data tree with the same structure that we want, then we also have to create something called path. So gh path, new gh path, and then we can use the I as the index, and then now we can say final points pts dot a maybe a range, because it's a collection. So we put TPS in here and then do path. So as an output, we output final points. So just to do things, you know, just to do things as these 4 components, we have to go through all this complexity, which is kind of difficult, right? If you are a designer, you try to do something, then this actually make your life really difficult. And this is where the no encode function can comes in to simplify the process. Okay, so now let's look at how to do the same thing with no encode. Okay, so let me just do the setup again. I'm gonna disable this, and then I'm gonna just copy. Okay, I'm gonna delete all these. Okay, so to use no encode, we basically need 2 functions. So one is find component function. Another one is to evaluate the component we find. Okay, so let's look at how we can write the syntax as a basic structure, and then we will start putting the information inside. Okay, so first of all, you need to make sure that you have this namespace Rhino.noEncode. I think it should be placed inside already. Okay, so once you have them, then we can call components, which is different from component. Component represent this C# script component, but component is sort of a method inside this namespace. So components, and there is a method called find component. Okay, so what you need is just the full name of the component. So we put it empty like this just for now. And then we can store this component somewhere. We call, the data type is called component function info, I believe. Component function info, and then call component maybe 1. It's like this. So just to be short, data I'm gonna just do var. Okay, so we have the component 1 from the system, and then the next step is to get the output. So we call OT1, and then component 1 is the one we found we want to evaluate. So we do evaluate. Okay, so this is a kind of a formula that you need to remember. So basically what it requires, you require the input of that component by using this object array. So you need to initiate the input, but at the moment, let's just keep it empty for now. And then the second input that you need to provide is, do you want to keep tree or not? At the moment, let's do true, we keep the tree. And then the last one is the output string. Basically, it will output a warning when something goes wrong. So now we need to create an output here. So I call W. So I'm going to put the string here. So this is basically what all we need. and we're gonna just reuse this infrastructure over and over to do most of the exercise. Okay, so now we have a component. First of all, component, and then component will find a specific component from the system. So for this case, we're gonna call circle. Okay, call circle with capital here. And then with this circle component, let's just leave it empty for now. Okay, and then we try to invoke this function. And as mentioned previously, this function was initially written in Python. So the syntax is a little bit, and to get the data up is a little bit different from what we normally do. We have to invoke the data to this method by putting this square bracket and put a 0 inside. Okay, so now if we look at A, now we should have a circle. And you probably will wonder, like, what happened here because this place is empty, right? So this is basically giving you the same behavior as how you normally do things in Grasshopper. So if we call a circle component, if you don't have any input here, then the component still work, right? Because it will just use the default data inside this component. So it's the same thing. So this gives you a flexibility, and also if you are not sort of experienced user, knowing like how to basically what kind of information you need to provide, then this is a really good way to do. And one of the reasons I prefer using Visual Studio, because I actually rely on these kind of auto completes and also those hints a lot. Otherwise, I cannot do anything. Okay, so now let's put something in here. Let's say point 3D and then origin. So we're gonna put the point at origin, and then we're gonna provide, okay, we're gonna just do this for now. So you see it work the same because the point is a origin. And now we're gonna change the size of our circle, change it to 10. You notice that now the size become 10. I'm gonna switch off this. Is this okay? All good? Okay, I will assume, yeah, all good. Okay, so now, and you probably will argue that just to create a circle, why you need to, you know, make things so complicated? You can simply just use a new circle function, right? So let's have a look when we continue. So what did we do next in the previous example? We divide the circle into series of points, right? And then we create a circle again, we divide. So let's look at how we divide it. So what I normally do is I copy and paste these two, just put it here. And this time I'm gonna call this a component 2. And then the component I want to find is called divide curve, okay, with capital D and C. Okay, and then output, I just change it to 2. And then the component I want to evaluate should be also 2. So basically evaluating this component called divide curve. Okay, and what kind of information I need to provide, because I'm gonna divide my circles into series of points. So what I want to put in is actually the output from the first components I extract, right? So I just simply put in here, and then I change this to 2 because the output I want to get is a series of points. So if you do this, then you get points. So just do this simple step. You will notice that in the previous example here, we have to handle this placeholder, right, called list. And then when we go to another layer, then we have to sort of deal with this complexity here, like the path data tree. Okay, so let's go even a step further. So this time I'm gonna do identical process, right? Create another circle on top of all the points and then divide again. So let's see how we can do it. Since we already find the circle here, we already find the divide curve component here, we don't have to do it again. So this is normally how I structured it. I will put all the component I want to find together, and then just put all the output together. So I would normally do this. So this time, what I want to do is I'm gonna put this in here, called output 3, and then I evaluate the circle component. The only thing I will need to change, okay, is the input here. So this time I want to put the output of OT2 into the input here. So I put it here. And then this time, maybe my circle should be a little bit smaller. So I give the radius 3. So I call these 3 as an output. Then you get bunch of circle. Now, if we want to divide, okay, we copy OT2 and put here and say 4. Okay, and then we keep it as a 2 because we're gonna use the same function, same component, divide curve. And the output here will be, the input here will be output 3. And then we call this time, maybe we divide by 5. Okay, and then the output will be 4 here. Then you get bunch of points out without handling any complex data structure. Okay, very straightforward.
Can I ask one thing?
Yes.
How are you syncing the code in the Visual Studio into a Grasshopper component?
Well, I'm using something called Script Sync developed by Long.
Oh, is it?
Yeah.
Is it like a plugin for Grasshopper?
I think it's his personal stuff.
I
Yeah.
see.
But if you guys want to use, I think there are some bugs. So that's why he didn't really release. But I can ask him. Yeah. Also, no, I also know Long quite well. So, yeah. Okay. So yeah, that's it. Any other questions? If I'm too fast, just tell me. Then I can slow down a bit. Yeah, because just try to squeeze all the content into about 2 hours. Okay. Okay. So
it's fine. Yeah.
If this is okay, now let's take a closer look at these 2 functions. Okay. At the moment, I just did something very quick. Since the function is very simple, 2 functions only, find component and evaluate. But what I want to look at now is to look at this find component method. So if we look at them, look at here, what it requires is full name. But how do we know what is the name of the component? Okay. So let me just remove this. Okay, I'm gonna go here. So we are kind of here. I always need to do this as a sort of manual setup. To that. Okay. So we are going to talk about how we inspect basically the name. So normally, if you are a sort of icon user, then when you suddenly need to find name, you say, how can I find name? But actually, it's very straightforward, right? So let's say I want to find the name of this component. Well, it shows here because I have this bifocal thing, so it shows the name. But the easiest way is to turn this into a text mode, and then you do full name. So you get the name of the component. And if you don't know if this really gives you the name of the component, you probably want to do something which is called reflection. You want to kind of investigate the internal data, right? And the easiest way to do that is to basically kind of use Grasshopper document. So we can select objects in the document, and then you return basically a list of elements, right? And then what you can do is you do for each. You basically, because it's a list, so you can just loop through by giving sort of iterator. So and just represent each name, each objects that you find. And what you find, what you want to do is to print out the name of the object. So let's say print the name. And then we can see if we get the name of the component. So now I want to inspect the name of this component. I select it and press down F5, so recompute, and then you get it. So let me just get a few more components here. Maybe a more complex one, divide curve. And I can select 3 of them together. So then you get the name. So this is kind of like a easy way to inspect. And then you can do something else. You can inspect much more than just a name. If you put the curly bracket here, and then we just make the code a little bit more readable. Let me just put it here. And then we do things a little bit like this. Okay, so now we are inspecting the name. What else we can inspect? We can inspect maybe the component GUID, and then we say to string. then you can get the GUID of each component. Okay, so sometimes it's quite useful, and you can do other things. For example, like finding where the component is by inspecting the assembly location. So to do that, we have to create a type TA equal let's say m get type, and then we can say print TA dot assembly dot location. So now we know where to find that specific components in your computer F5. Again, now this item belongs to this math component GHA. Okay, so it's quite easy to do this kind of inspection, and it's quite useful. However, you might notice one thing when I click this divide curve component, and you notice that the name shown here is actually different from the name we used before. You will notice that previously when we do this divide curve, the name is sort of like a link together, right? And so this actually caused some confusion for people who use it in the beginning, because sometimes you find circle and it works, but you find another component, it doesn't work. That is because this no encode is using a little bit different naming system. And the reason being is because this function allows you to access all the components in your Grasshopper. So it has to find a way to distinguish the same, let's say the function with the same name. Okay, so to do that, I'm gonna just remove this, and then we have this using Rhino no encode here. We say components, okay, because we're gonna use the no encode components, and then you can use this function called no encode function, and then we can get this get dynamic member names, okay? And then let's just output it for now. Maybe let me store in, what is the variable here? O, okay, so I'm gonna do O. Maybe just names first, and then output in O, sorry, not this one. O equal names for now. Okay, so names. Okay, so we have a lot of components here. If you look at my parent viewer here, it's good that we can find all the components available to us. However, in this case, it's not really helpful, right? Because I have 2,568 components in my Grasshopper. So if you want to scroll through the list to find a specific components, then it's gonna be headache. And you notice here, like this pufferfish component, it has this sort of underscore here to chain with the function here. So this is how no encode differentiate the native function and the third-party plugin, and also this allowed you to call third-party plugins. Okay, so we have to create some sort of filter to basically let us narrow down the list a bit. Probably you cannot really narrow down to just one, but it can at least narrow down a little bit. So let's try to see how we can do that. So we have names, and if we want to filter, we can use this function called where from system.link. Okay, and then what we are going to do is to filter the information. Okay, so let's see how we can filter. Let's say name. I'm gonna filter by the method called content, and then I'm gonna do maybe what I'm going to do, divide, maybe divide. Okay, and then I'm gonna just put into another variable called maybe select names, maybe. Okay, and then I'm gonna output in this s name. So basically, just represent select name. Oops, select names here. Then, if you look at here, how many do we have now? So basically, the list is narrowed down a little bit. So it basically shows that all the components with this divide text inside. However, you will still find this method has a bit of problem, because when you are not really sure about text. So let's say if you put the divide curve, okay, now we still have maybe 9 with a small d here, but then you probably eliminate some of the component you want to find, right? Just because you don't know if the text should be capital or should be sort of in lowercase. This is where we can probably use the method to put them into like a lowercase. So all the name we find will be in lowercase, and then we also put this in a lowercase. So something like this. So in this case, even you have some really weird sort of typing, let's say DI I in capital, V in capital, you can still find the name because whatever you put in here will be cast into sort of lowercase. So this is quite useful. And what I normally do is I normally provide, instead of providing one string, I provide 2, because one is for searching, for instance, like a specific type of, let's say, third-party plugin. So you say maybe a Launchbox, you want to look at all the function just within Launchbox. And so the example here is this hexagon cell. So what we are going to do now, I'm gonna just bring this one here a bit. So I'm gonna change this a little bit, change it to ST1. So that will come from Grasshopper. And then what I'm going to do here is I put this end here, and then just copy and paste this again and change this to basically ST2. And then let's have a look. Oops. Again. So now you see the list is further narrowed down into 2. So we find, first of all, everything with the name Launchbox, and then we find the name like called hexagon cell. Okay, let's say we want to get that. And sometimes you still get the list probably like 720 or something, and you want to quickly copy the name. There's another way to do, not just copy the whole list or retyping everything. You can use the index, right? We can say maybe the cell names here, we can use this method called element at, and then we can put in the index, which I have the variable set up here. Okay, so we can call the index, and I'm gonna just print the whole thing here, like this. Okay, so then you see the index is 1, so we are printing this. So now you can easily just do copy data and then just put into the no encode component. Okay. Okay, all good? Yeah, okay. Then if it's okay, then we can move on to do a little bit more complex exercise, right? So now we can look at how to create this. Now it will become very straightforward if I go down a little bit. So to look at this. So this example shows that here we have this Centerbox. Okay, which is a native Grasshopper component. And Populate 3D is a component that is not documented. Rhino is not documented. And then it's a little bit difficult to implement. And then this is third-party plugin. And also, at the time I was using Rhino 7. So this is a subd component. But we can use a Weaverbird or whatever to replace that. Okay, so normally if you want to just do this in C#, it's gonna be quite a headache. But now it become very simple to do. Let's see. I'm going to call my Grasshopper back and then do a little bit of setup here. Well, I'm gonna change it back to just icon. So it's gonna be here. I'm gonna copy and paste this. And then gonna relink, change docket to that. Okay, and then gonna just do this too. Hey. Okay. Now we can quickly, okay, so since I have all the text set up, then what we need to do, we can quickly just copy what we did before, right? Here, we copied everything here. Maybe just two of them. Okay, we copy the syntax here. I'm gonna change it back to icon. Okay, so this time we have how many components? We have 1, 2, 3, 4, 5, 6. So we basically need to call 6 components. So we're gonna do this have 6 of them. So we quickly change it to component 3, 4, 5, 6. Okay, then we also need 6 of this, right? So that's just copy and paste. Okay, 1, 2, 3, 4, 5, 6. Make sure you also change this because sometimes you will extract the wrong component. 2, 3, 4, 5, 6. Okay, so let's look at these basically one by one. Okay, so first of all, I'm gonna put ST, which is set up here in here. Okay, so we can quickly just put this here, ST2. Gonna copy this. Okay, we have everything in, and then we have an arrow. Let's check. What is the arrow here? 71, 71. Okay, yeah, that of course, because this is the wrong input here. Okay, so what is the first component? The first component is Centerbox, right? So if you're not really sure what to put in, you can simply just call the component out. Centerbox should be in surface. Centerbox should be here. Okay, so basically it requires a few things. It requires a base, which it can be a point because you normally put a points, or you can put this plan in. Okay, let's just do it properly. Plan, let's say words XY, and then we can put in, if you don't put anything in, it still work fine. Let's say OT1. Here, wait a second, SD, I still have arrow. 71. Component 1, component 1. Let me see if I put in all the information. So to inspect that, there is a way to see if you find the component correctly. Let's say if component 1 equal new, and then you basically print the name. Print, let's say component 1 maybe. Oops. Okay, so com1. So what this means is there is a problem with the name. Centerbox, that is Centerbox. Component, let me see. What happened if I'm going to just put Centerbox? So if I put Centerbox, okay, so maybe the name is not right. String, Centerbox. Not quite sure why this is not working. Center, let me just put it here. ST. It should be okay. It's a little bit weird. It still show me the arrow. Centerbox here. Do you guys have the same arrow? ST. Find components.
I think without this, how to say, this chong.
Oh, I know why. Because okay, here, because I put the string into this double quote. Okay, here, just remove this. Sorry. Here, okay, so it should be working now. Let's see. Okay, great. So now it's okay. So then we can just put this out. Okay, so that we have a box, and you can change the dimension here, 30, 30, 30. Okay, something like that. Okay, so let's just try to place this in one by one. So here, the second function is basically populate 3D. So what it requires is the box. So the box will go here into here. Okay, which is okay. And then let's say output 2. then we get a bunch of points. At the moment, by default, it's 100. That might be a little bit too much. Let's say maybe 30. Okay, so we get 30 points inside. And what is the next? The next is Voronoi 3D. So Voronoi 3D here basically require points and box. So the point will be the points that we just generate here, and the box will be the box we generate for these outputs, right? So let's just do here. So points will be here. We simply just put in here, and then we put OT1, 0, and as an output, this will be 3. So now we have a Voronoi, and then we can just continue this exercise, putting the 3 in here. And then, okay, let's do it like this, and then put OT4, 0, and then look at OT5 here. Okay, let's have a look. So at the moment, you notice that if we get, what is OT5? OT5 is basically this plugin called Fatten. It's sort of plugin to join all the mesh together. But you notice that my mesh, they are not joined together. And that is because at the moment, my data structure is set as sort of a true. So it's basically a data tree. So if we want to put them together, we have to want to put them into the same list. Then we can change this to false. Okay, wait a second, that should come from the cells. Wait a second, where is which one is cells? This one. Okay, so we have to go one back here. We set here, this is false. Then you notice that now they are all joined together. So if you put the geometry into Weaver, then you get a kind of nice, smooth geometry. Okay, so I'm gonna put this here. So as simple as that, and then you do maybe 3. So to do a Voronoi kind of geometry, it can be as simple as this. So it's quite convenient. So I mean, like to just do things like what we did here, in general, it's quite complex, especially if you want to do a kind of additional logic on top of this. You first of all have to implement everything to get to this stage, then you can do something else. But with this no encode function, is extremely fast to get to this point so that you can do whatever logic you want to do. So, okay, that's good. So as mentioned previously, no encode function allow you to do things in a very convenient way, which you don't have to handle too much about input of data. You don't have and data type, and then you don't have to worry too much about data structure. But there are some occasions where you actually want to do some kind of data structured operation, especially when you sort of not in a kind of a pure no encode working environment. So at the moment, we are only working on one object, and then the object is always generated through this no encode function. But in some circumstance, you want to sort of like work in a more kind of hybrid way, because I will tell you, I will show you an example show this. So this is where we have to look at how data structure work in Grasshopper. Not really in a kind of script environment, because Grasshopper data structure has a different sort of setup. And then when we talk about data structure, we mainly talk about these 3 things, right? One-to-one relationship, one-to-multiple, or multiple-to-one, and multiple-to-multiple. And what that means is how we basically handle these things called branching item relationship, how we do this kind of mention. But this Grasshopper data structure is always a very confusing topic. If you look at this page, we have basically a set of component 1, 2, 3, 4, 5, 6, 7, or 7. They are basically all the same. Essentially, and in terms of the geometric outcome, they are also identical. However, if you look at the parent viewer closer, you will notice that from the branch and item, they are kind of identical, but from the path, it's a little bit different. And normally we kind of ignore that. But I don't know if you've ever wondered why it creates this kind of difference. So for instance, if we look at just the first one and the second one, we have one input to X and 3 into Y, and then you get just a path with 1, 0. But here it's the same thing. You have 1 here and you have 3 items here. You put in here, you get 2, right? It's a little bit confusing. And as well as this, this is another example where the geometrical outcome is also identical. We have this rectangular geometry, but this component has the ability of creating basically a matrix of this rectangular shape, whereas this one allows you only to create 1 if you don't do a kind of additional logic to that, right? But if you look at the output, it's kind of same, but look at the path, it's different. So let's look at how things work in general. Okay, this is my sort of my understanding. Maybe everyone has different take on, but okay, let's look at this sort of diagram. Let's say we basically start from the left all the way to right. And in Grasshopper, probably the most basic things could be a number, could be a Boolean toggle, could be some sort of things as simple as that. So in terms of the most basic data structure will be one branch, one item for sure, because it's only one data, and then with the path with just simple 0. However, when you pass it to a point, you notice that actually you are sort of assuming the complexity increase, but however, the data structure complexity doesn't increase. It still sort of stay the same. And then you sort of put it in to transform that into a line, and it still stay the same, right? And that is quite confusing, right? And I normally consider this as sort of casting or representation process. So in a way, of course, from the memory space, that is different, but sort of in the Grasshopper perception, somehow when you transform one object to another, that the objects that you sort of transform, that is a representation of the previous one. So now we have one point, that point represent that number, and this line represent that point. And then when you get a point, this point represent that line. And when you get to even 2 outputs, because it's a separate output, then each point represent the previous geometry. Okay, until you get to the point where you start having multiple outputs, then you notice that the data structure start changing. And this is kind of important, especially when you work in a no-encode environment, because you basically inherit that kind of behavior, right? So when you purely working in that environment, so you have to use your imagination a bit to understand how things change when you have to do a bit of matching. Okay, and then you see from here to here, because each sphere represents each point, so data structure also remain the same. And when you go to another level where you basically try to squeeze more points, 100 points into each sphere, so this is where the data change. So if we look at this from sort of kind of source code point of view, and you will find something also quite interesting. Maybe that explains the reason why this change. So if we look at this curve point at method, and you notice that the input require a t-value, so that t-value represent the position of the point on that curve, right? And that point is extracted from the curve. So in a way that represent that. So in a way, they are sort of like a kind of with the same form in a way. However, if you look at this curve divide by com, the output of your point is actually a new collection where you have to always create outside, right? So here, when we try to say, okay, this point represent to that, but here you actually cannot say a specific point that represent this line. It's a collection of points that represent the line. So in a way, you sort of save all the points in a new collection where represent by a sort of a new memory space. That's put it this way, right? So this is where things change. So just to put in short, whenever you have one input that generate multiple outputs, so that your data structure transform. And then another scenario where data structure transform is when you do some sort of list and tree operation. When you do, for instance, like flatten, graph, shift, all sort of things, then your data structure transforms. So if you keep these two principles in your mind, then when you start training up all the components in no-encode space, then it's pretty much easier, I would say, not easy, but easier to kind of trace back what kind of data structure you will get through the process. So refer back to this example. So basic, what this component does is actually this, right? So sometimes you will say, oh, why the matrix is in this direction, that direction, not starting with that direction and that direction, because this is essentially what it does. It basically moves in X direction, and then it sort of graph into a sort of a separate branch, and then you go to in Y direction, right? So if you look at the source code, and you will notice how the structure is sort of created. Okay, so now let's go back to no encode and look at what happened here, because this is a very interesting scenario where you probably don't see any problem just when you first look at it. But if you look at closer, look at the Grasshopper and look at the script, you probably will find something a little bit weird. So first of all, if we simply look at the no encode function here, the one I highlight with kind of a red box, false. Remember, what is this? This is to control the data flow, right? Control either we get sort of a data structure, or we have a flattened kind of a list, right? But somehow the data we get here is sort of a data tree. Do you guys know why? It's a little bit weird, right? And this is actually to do with something quite sort of simple, but we always just take that from granted without thinking too much, which is the data access. So data access, there are three different ways to control your data when you are dealing with this kind of script component, which is item, list, and trees, right? And what does it really mean? By these three different types. In principle, we know that when we have one item, we use item access. When we have a list, we do list access. When we have tree, we just do tree. It's as simple as that. But what happened behind the scene here is item access. When you have one item, so everything here, that will be executed every time. And when you have a list, the whole list will be executed every time. When you have a branch, each branch will be executed every time. So what happened if you have 10 items here in the item for this one, for this input, without setting this into these assets? What that means is this code will be executed 10 times. Let's say if we have 10 items here. So if you have a component not take into two inputs, so let's say this is the first input, this is the second input with different sort of assets sort of setup. So you have item assets here, and you have this item here, but they both have 10 items each. What happened is you sort of create a condition where you have a basically a cross reference, right? Because what happened is you have 10 items here. Every time the script will run once. When you run once, 10 items will be executed altogether. When you run the second time, those 10 items will be executed again. So in the end, what do you get from here? You actually get 100 items instead of 10 items. Okay, so if we come back here, so as the input data form, that is a branch. 200 branches with 5 circles in each branch. And then here, what this component does is to divide those circles into series of points, and each circle is divided differently here through these random components. You generate maybe 4 number, 3 number, 2 number, or whatsoever. But however, when we put them, basically put the data structure in here as a tree, as you can see, but without setting things as a tree, what happened is, because the item, remember what I say, what item is executing each data, like every time. So what happened is, even we have a tree structure here, what it does is to take out one circle and try to match one and get the data out. So one circle, and maybe the first one is divided by 4, so you get the first circle. Okay, and second, you do that, you do that. So even you do this false, that is the default behavior right? It's a default behavior which you don't concern about any data structure, because the data access is item access, so they will just process one by one. So even you set this as a false, then you still get the tree data structure. This is something become a little bit interesting and can be something useful too. And then whereas this you said true, so everything become flattened, because the previous one is a default form of the data structure you get, and this is actually how you break it, right? Okay, so if we look at the data semi example in the sort of data tree and this match, and you will notice that now here we have a data tree here, so 20 branches with 10 items each, and then now here we have 10 items here. So if you try to match every time you execute a branch to pair with the list all together. So as a result, it stays the same. Okay. Okay, so we've been talking about how data structure transform forward. Now, sometimes in some occasion, when you have to separate like upstream process, then you might get different lengths, right? And then how do we deal with this in sort of no-encode environment where you have to do this kind of matching? So, for instance, like you have to go one step back. In Grasshopper environment, we can do things like you know, kind of twin tree, right? So here we have bunch of points within this big chunk, 0, let's say, and then we have 11 basic sub branches within this big chunk called 0. And if you want to go one step back, you simply just trim the tree down in one level, so it go back all together. So now here, if you look at here, we basically have 3 chunk. If you go one back layer, 11 chunks actually. So if you go one layer back and go back to basically 11 let's say sub branches, and if you go another layer back, everything go back to the main chunk. So this is how you can control this kind of behavior within a no-encode function by simply implementing twin tree if you want to sort of go one step back. Okay, so talking about all these, then we will soon look at an example to deal with the list. And before getting to that, another things that I would like to mention, which I kind of touch on a little bit, but not in detail, which is this data type called Python runtime list. As we know, no encode is written in Python, so that's you get this kind of weird type. So at the moment, when we process things in sort of a pure no encode environment where it doesn't really care, because you sort of like interchange data between this Python runtime list and Python runtime whatever. So you don't get any problem. However, when you start doing this kind of hybrid sort of match, then you immediately get into the problem where you're gonna exchange data. However, it's actually it's not complicated to deal with this problem, because this data type implement all this interface where allow you to sort of iterate through each elements, and then you cast to the right type of data, which is what we are going to look at soon in the next example. So here, just show you a case. Here we have a false. So by default, it's gonna be a list. So you just cast it into the list object type, and then if you want to extract points as a result, you simply just cast to a point. So same for the data tree. So if it's true, that is always a data tree. So you can sort of remember that. And then if you want to cast it to just a normal data tree, then you just do that as data tree objects, and then you can iterate through by the normal method. So let's look at this example. It's an example I think quite interesting to look at in many aspects. First of all, to do this in the pure Grasshopper environment, you probably need to do all this, right? And then if you want to do in script environment, which you have to plan a little bit how things connect together, which is not really straightforward. But with no encode, you simply just call this component out, and then you can already do the things. And another aspect of this example is when you try to get colors to each component, sometimes with one color, you don't have problem because you basically just assign the color to all the elements. However, if you want to match the number of, you want to have all elements with different color, then you have to do this calculation internally, right? Because you wouldn't expect the number of elements you will get, especially when you work on maybe like a Voronoi or something. It depends on the position of point and you get a number of cells in the end. So you wouldn't expect that. So this kind of calculation has to be done internally, right? So this is where this kind of sort of a hybrid process comes in. So now let's go back to Grasshopper and look at how we deal with that. Let me see what is that. Okay, should be this example. And then I'm gonna do the bit of setup here. Okay, I'm gonna remove all these. And then gonna grab these things here. Okay, and then do the usual way. Hey. Okay, now we can stop. Okay, so first of all, we have let me just turn off this. We don't want to see everything we don't want to see. Okay. So first of all, we have a surface, and then to basically call the component out, it's quite straightforward, right? Actually, maybe I shouldn't just. Okay, I'm gonna just do it from scratch. Find components, and then we're gonna do this. And then I'm gonna call this component. This is in where in ST. So we don't need this. Call ST, and then we say component one. Okay, and then we can do this too. OT1 equal component one. Evaluate, and then create objects, and then say false for now, and out W. Okay, so we can invoke this one by giving this surface SRF. So we should be able to get a hexagonal grid. Oops. Okay, so it's as simple as that. Then let's maybe give a bit more division. Okay, so we can control that maybe even from UV here. Actually, UV. So we can just simply just drop this. Okay, so now we have a bunch of components. We're gonna just put them into a mesh pipe. So we need another component, component 2, called, do I have that mesh pipe somewhere here? Oh, here. This is ST2, okay, ST2. And I'm gonna copy and paste 2, and then put this in. Let's see if it's gonna be a bit too big. Okay, it's too big. Let's give a smaller radius, maybe 0.5. Okay, so it looks perfect. So now, yeah, we basically get the geometry out from this process, and now we want to count. Let's say, if we want to do this mesh color, which is the third component, and then with all different colors. So first of all, probably the first thing in your mind will be just generate another list of color, and then just put them into the component. Let's try that first. So first of all, let's create a list of colors. Okay, so now we have OT2. We want to count the number of components inside. We have first of all cast it to iList object. Okay, so we put this into something maybe called OT2 convert. Sorry, I'm really bad at naming. I always use just random name. Okay, so put it into IDs, and now I can iterate through. the list, okay, for each, okay, for each. Let's say give another name, she in OT2 she. Oops. Okay, so now we can create color. Say color and new, sorry, color. And by the way, to do that, you will need system join here as a namespace here. You will need that. Okay, so color we say from RGB. So we need to create a series of RGB value, and then we want them all to be all different. So we have to maybe just make a sort of a random generator, new random, and then every time we want this to be different, so let's put a counter here, and we don't have a counter, we create a counter here. Okay, and then so every time we can generate kind of random color. So this RG dot next, say between 0 to 1 to 55. So for instance, like this. Okay, so let's just put in here, here, and here. Okay. Oops, color. Maybe one more. Okay. So we create basically every time we create a random color, and now we want to put all the colors into a collection. So let's call a color collection colors maybe new list color, and we're gonna put all the colors in. So colors dot it cool in here. Okay, so now we have a collection, and then we can sort of call the third component here. Component, the third one. Let me see what's in it. ST3, I guess. Yes. Okay, so change it to 3. So we put it here. Okay, so output 3, we evaluate the component called mesh color, and then we are going to put the output from the output 2 in here, and then we put collection of colors in here. Let's see what we get. Okay, so OT3. Okay, at the moment it's a little bit hard to see, but you basically, let me see if I can see this properly. First of all, I want to also maybe print a list of color to make sure that they are all different. Okay, they are all, okay, here counter, my counter need to do ++. Okay, so now you get this kind of funny result, right? That is because in Grasshopper, some of the component that basically require, normally when we try to match stuff, we as long as we match the right branch and list, that works fine. But there are some components which require this kind of one-to-one match. So in this case, you really have to evoke these things inside the loop, and then try to do this match, right? So we can simply put this in here and say we put this in here. We add, we can just ignore that. We don't need to look at the color because we cannot do the color here, which is called CO call. So we try to match it here, and then we try to invoke the geometry here by coding this here, right? But what we want, because we are staying in the loop, so we have to basically put it outside. So let's create a temporary sort of storage, let's say. This we call, and just do it quick, say final mesh maybe equal new list objects. Okay, because I'm not going to do anything on that object, so I don't need to convert to the right type. But if you want to do something to it, then you need to convert to the right type. At the moment, I don't need to do that, so I will simply just convert this into objects by doing this OT3C convert into that. Okay, and then I can say final mesh dot add range, and then put everything in here, and hopefully this will be working. Let's see. So now we get some kind of funny result. Let's see what happened here. So we have object random color. We put the color in here. New objects, 3, evaluate OT2, which is that one, that is this one. Let's see what happened here. Well, we only get one color, and also we probably get too much data here. Okay, because okay, here, because this is gonna be sort of a list, and then we know that in each we have to actually we need to extract one element. At the moment we are putting the entire collection here. Okay, so what I'm going to do, I'm going to sort of I think I can also do this, and objects cast it into that. So for these elements, I have that. What I'm going to do is to do this, and then I can say counter, I believe. Oops. I get the counter one objects from the list and try to match that, and then hopefully this will work fine. Okay, so now this is now we get basically one color on each cell. Okay, so this is the scenario where you have to sort of do this kind of hybrid kind of matching and using no encode function with the sort of a traditional kind of programming method. Okay, and the way to do that is you have to invoke your geometries and then cast it to this type so that you can iterate through. Okay, any questions? If not, then we can continue. So since that we almost covered all aspects of this no encode function, now we can look at a slightly more exciting example, because what you probably notice, no encode is extremely good at kind of doing this kind of data, handling this data structure and also the data type. So what I want to do is to look at sort of an exercise that combined with this kind of approach that's simply based on a combination of elements, as well as this kind of iterative process where you can sort of do both generating things in a sort of growing kind of manner, but at the same time, it has a capability of combining in different way. So that is a little bit similar to these things called L parser, which is quite interesting things. You can see this probably like more in nature. So you start with one elements and they start growing, and depending on different condition, and it not only just transform, it start doing different things like growing this kind of like a green things, right? So that actually give you a lot of sort of imagination or potential how you can actually grow things or do things in this kind of button up method in a sort of between control and non-controllable kind of manner. Okay, so let me just go back here. So the exercise, we are not gonna look at that complex exercise, but we look at something a little bit much more simpler, which we look at only two set of element, two set of kind of function, which this is one cluster with the same type of geometry. Here is rectangle, circle, and polygon. And another type of another cluster is like points. Basically, what we want to do is to form a new function through the combination of one object in cluster A and one object in cluster B. So basically, we extract, let's say, A1 and then try to pair with B1 to form a new function, or we do A1 and pair with B2. So we basically have 9 combination simply from this simple example. So the input is just a simple point, and the output, you can imagine, it's going to be quite dynamic. It depends on which function you choose. And then what we want to do is also to do this idea of iteration. We're going to feed all sorts of points coming out from here all the way back here to form another iteration. And as a result, you will, first of all, we're going to separate into like 2-3 parts. The first part is to generate sort of a two-dimensional shape language, like what you see here is a little bit messy, but I mean later on you can make it nicer. And as you can see here, so based on different level, you have different combination to generate that. Okay, and then for the second part, we're gonna sort of implement this kind of L system logic by connecting different points together to form a three-dimensional object like what you see here. So in a way, this object represent that object. So it's kind of a fun exercise we will be looking at now. Okay, so let me just go back to Visual Studio. And so you can see, maybe let's have a look at this one first. Okay, so here, if I go here, so this is only one generation, one iteration. We don't have any feedback loop here. But if you try to adjust this random seed, okay, it's the same iteration, but you basically have different selection. Yeah, you different selection, so you basically get different outcome from it. And apparently that you can assign different sort of geometry to each point. Okay, so we're gonna do this first as the first step. So I need to do this again. Okay, I also want to put this in here. Okay, so you guys should all have these things set up. Okay, so good. Okay, so first of all, we create two sets. Let me just make it slightly smaller. You guys can still see, right? So here we have two sets. So I call it A1, A2, A3. That is basically the first set of geometry as I show you here, cluster A. And the second set will be B1, 2, 3. And then we will look at this in the end to do those kind of complex stuff. And here, what I want to do is, first of all, create a collection, maybe called group, to put them together. Okay, so let's create a group. Let me see. We can say group object. It's an object type, and then we're gonna put A1, A2, A3 in, and then we just name this as SG1. Okay, so that is our first group. New. Okay, here I'm gonna copy and paste here, and then say G2. Whoops. G2 and B1, B1, B2, and B3. So what I want to do now is to basically create a selector, okay? Like what I show you here. So we have a selector. So every time we generate a number that can select one of the objects here. So that's called, let me think about something. RG1, random generator, new random. And at the moment, we just give maybe a random number like this. Okay, and then we create another one called RG2 and say maybe 7, something like that. Okay, and then we can generate a set of numbers that's called R1. So RG1 dot next, and then say between, because we only have 3, so say 0 to 3. Okay, and then we do the same thing for the second collection. Okay, so now what I want to do is to extract one of them from the collection. Okay, so I'm gonna do this. We need to first of all do, let me call this as a obj1 or object1, and then we have to cast this into component function info, because this is how we can evoke the function from this no encode, and then we say G1 is the first collection, and then we say R1. Okay, so that is the first one, and then we do this object 2, and then 2, this should be 2. Okay, hopefully we don't have any error so far. Okay, so if we try to print the name, okay, without doing anything, let's just try to verify if we have the combination. Let's say maybe 0, okay, plus 1, and it will be obj1 dot name, and then obj2 dot name. Okay, let's print this first, see what we get here. So based on the first iteration, okay, now because we haven't assigned anything, I'm gonna just grey out this for now. Okay, so the first combination we get is polygon divide curve. Now we can make it more dynamic by controlling from this slider. So ren d, we can just simply do a plus here. Okay, plus ren d. Okay, ren d. Okay, so now if I move the slider, we should have different combination. Okay, so that's great. So it's working. So what we need to do now is to basically transform those texts into actual geometry, right? So what I'm going to do is, okay, let's just do it without loop first. So obj1 evaluate like what we did before, and then we're gonna create new object, and then we say false for now. And then what else we're gonna do? We say out W. Okay, so we have to put this back. Okay, and then we have to put this back. Here two. Okay, so empty, and then we can call this something else. Output 1. Okay, and then this will be output 2. Okay, so what would be the first element? So since our geometries are all taking a point to begin with, so we cannot fit in a point. And as we know that in Grasshopper component, you can put in a list of points. Oh, my video camera. Wait a second, let me put it here. Okay, so in Grasshopper, you are able to basically, let me, wait a second, here. Okay, so in Grasshopper component, you are able to provide either one single item or multiple item, or even with tree. So since we are going to iterate through, so we will put all the collection of points in. So what I want to put as a starting point, I'm actually gonna put 1 point, but with a sort of a list kind of format. So what I'm going to do here is I create something called maybe points equal new list point 3D, and then I put 1 point in there just for now. Okay, so I can put points in here, put point in here. So 1 point in, and then we put the outputs of that into the second collection, which is 0. And as the result, we get outputs from 2, I believe. Okay, let's see if it works. Okay, so based on the first generation, now it's a polygon. Okay, maybe it's much easier to see here. It's a polygon. How many sides we have here? Okay, so it's a polygon, and then with this divide curve component, if you want to verify, you can do things like that. I believe that you get that. And then if we try to change this, you basically have, wait a second, oh, of course, this is not gonna be the same. So this one is circle with divide curve. So basically you have different shape combination. Okay, so sometimes you get 1 point because if you have a rectangle with just one endpoint, you get 1 point only. Okay, so now we know it's working. So we're gonna create a loop. So every time when the points are generated, we're gonna place them into the collection here. Okay, into collection here. So we need to create a for loop somewhere here. Let me just put. Wait a second. I'm gonna put this outside the loop. Okay, so for loop for integer I equal 0, and I we have okay, we have a number. This we gonna use this number as iterator. Okay, I smaller than number, then I plus plus. Okay, we're gonna do it like this, and we are going to put everything in here. So we probably don't have this for now. Okay, so we're gonna run through maybe 1, 2, 3 different times. So we need to do a bit of modification on the code here. So every time we run, first of all, we want the numbers to be all different. So I'm gonna also plus I. Okay, so at least these two generator, they're gonna have different numbers. Okay, and then we do the selection, and then we get all the points here. But now we have to get the point out in order to put it back, right? So we have to do this OT. Okay, do it from here. OT to C convert. We convert OT to 0 as I list objects, because we want to iterate through, and then we want to create points, right? So this is where we have to do this. Let's say P in OT to C. Okay, so inside this collection, I want to create maybe call points new, and we cast this into point 3D P. Okay, and then we can, okay, at the moment, if we want to so at the moment we get all the points out from this OT2, and then we have to store those points somewhere here. Let's say a temporary point list, 10 points equal new list point 3D here. So what we want to do is to store those points in here. 8 points. So it will be the point 3D types. And then what we are going to do next is to replace these things here, which is the one that we did here. So PTS equal new list point 3D. Okay, point 3D, and then we're gonna put these temporary points in here. Okay, and at the same time, I also want to, because this is just to put the latest generation into that. So what I also want to do is to keep track every iteration. So let's say the first one, we can actually print this probably first to see what we get. PTS. So we do that. Let's see, 1. So here we have 1 point. That makes sense. Okay, if we do 2, we should have more points. Yes, because it's a combination of that. 3 points, we have more points. That makes sense because, yeah, because we have a rectangle and have different control points here. Okay, so it's kind of working. Okay, so now what we want to do, but you notice that everything is generated in one single list, right? If we just go through the iteration here, It's one single list. But if we want to create some sort of network, it has to be based on sort of generation. So to do that, we actually need to create another placeholder, and it has to be a sort of data tree. Okay, and let's also use this called point.
Sorry, can I ask you one question?
Yes.
When you were casting a point P to a point 3D on line something like 100.
Here?
Yeah. It says I got some errors saying that the specified cast is not available for line 110.
Right. Did you do this first?
Yes, I did. Yeah.
And then when you iterate through, do you iterate through this or do you iterate through this one?
I iterate through OT to C.
C.
Yeah, that one.
I have the same error.
Okay, if you have the same error, maybe it shouldn't be. On this, okay, what is the data? What is the tree control here? Is it true or is it false?
It's false.
It's false, so that should be this for sure. And if it's a list, then you should be able to cast it. Okay, let's try another way to do that. You can simply do this here and then call cast it to dynamic.
Okay.
Dynamic. Can you try this?
Okay. All right.
Oops, I get some funny error. OT2 here, P. OT2 here, P.
Now it says
It's still the same.
I got the different kind of errors saying you cannot convert geometry.circle into point 3D.
You cannot control. Sorry, you cannot convert what to
Geometry.circle to geometry.point 3D.
It shouldn't. It circle. So where do we get? Okay, so when you evaluate, are you evaluating the right one? So 2, and you put in
yes.
1.
Yeah.
I
think so.
Not quite sure. Probably need to look at it.
All right.
Yeah.
Should I? Well, I guess I can just see it later. You can continue. If anyone having the same errors.
Right. Okay, wait a second. Now it seems like this time I also get some funny error here. Let's see what happened here. I did that to OTC, and OTC you should be able to. Okay, that is not PT. Is this the error you get? Okay, wait a second. My error is a little bit funny because was using that and my data tree disappear. Or maybe I just didn't finish. Let me, oops. Wait a second. Okay. Should I continue first, and then we can look at that problem later?
Yeah.
Okay. So at the moment, now I create a temporary tree here. I create a temporary tree here, and then I'm going to store my elements into this data tree too. So here we store the points in here, which will be used in the new kind of iteration. But at the same time, I want to keep track on all the points. So what I'm going to do is pt tree dot add actually, I'm gonna do it outside. So I create a new gh path. Path. and then it will be based on the iteration, So now I can do pt tree here, dot 8 range. I'm gonna add everything into the tree. Okay, so here gonna be temps and then path. Okay, and I want to output this one in B, pt tree. Let's see. Okay, so 1 iteration, 2 iteration, 3 iteration. So that's good. So now we have basically different number of points in different different basically generation. Okay, so now if we cast this again into a shape, so for instance, if I'm gonna create another maybe random generator, just for demonstration, 3 here, and then I'm gonna use extract the same thing here by calling this. Let me see. Okay, maybe we'll do this later. So now we have a set of points, and what I want to do is to basically move them up and down. Okay, so give them a little bit of dimensionality. Okay, so here we have points. To do that, it's actually quite simple, because what we can do is just to create another random kind of value here. So we say rg maybe 3 here, new random, and then I'm gonna put a counter here, and then we put the integer counter equals 0, and just to remember, I need to always do this. So the counter will be different. So and rg3 dot next double, and then we say maybe minus 0.5, and then we can times the value. So we can control how much we want it to move, maybe 2.5 times, and then we put it into a double called height. So now what we can do here is we can add that number, add a new point 3D. That's called 0, 0, and then high. Okay, we do this and then see what we get here from 3D view. So now we should have them move sort of up and down in sort of 3-dimensional space. So the next step really, so we pretty much finish this 2D exercise, apart from just casting them to different shapes. So basically what I did there is to just go through another iteration and extract different shape to put on each point. Okay, so we're not gonna do that now. What I want to do is to create a sort of a connection between all the points based on different generation. So by using this method called close point. So if we use this, we go in this direction, then the result will be only 1 point, basically, right? So because this generation has only 1 item. If we go this way, we're gonna extract only 1, because we extract the closest one. And then we're gonna go here, we're gonna extract 1. So as a result, you only have like 3 points. So instead of doing that, we're gonna do it in opposite way. So how can we do this in opposite way? We just need to simply change one thing. Okay, we just need to go back to our path. This is how we define the path. So if we do number minus I and then minus 1, so this will become different, become this direction, right? Because the first one will be basically become the last one, right? In total, we have generation 3, and then minus 1, because we always have to be mindful with this 0 index. So minus I and minus 1. So when you iterate through, then we put it in sort of a backward. Okay, and now what we can do is we have everything pretty much prepared, and then we can just process the point tree collection. Okay, so what we want to do is to run through each branch and try to use the function called close point to extract a point and then link them together. So here we have few functions here. One is close points, and then we create a line. And the reason in this context I use that because then we don't have to care too much about data type conversion. And you can apparently do all the sort of IDs things and run through each points and then do the connection to become the normal line. But here I'm gonna just use that, and then I'm gonna put everything into sort of a flattened list so that I can do the exercise like what we did before, and then I'm gonna turn into kind of a funny kind of organic geometry through Weaverbot. Okay, so what I'm going to do is I'm going to do a for loop. Okay, for loop. So we know we have number, and at the moment we have to do this minus 1. Okay, we do minus 1, and what we want to do is to iterate through the branches. So we're gonna call this first. Okay, OT3. Okay, and this will be CP, I believe. Let me just double check. CP, okay, close point. And then close point. And then I want to set this as true because I want to keep the branches, the branch structure, so that I can later on do the link between one branch to another. Okay, so now I need to get all the items in the first branch. So it's PT tree dot branch. So we get a branch, and then we need to extract things from the path. So we do PT tree dot path, I believe, and then we do the first branch. Okay, we do the first branch like that, path. Okay, and then so this one will need to find all the points in the next one. So all what we need to do is to copy this and do I plus 1, right? I plus 1. Okay, and what we are going to do next, since we find the point, close point here, should be somewhere here, close point. So we find the point from basically the next collection. So we also have 50 points here. What we want to do is to link this one and that one together. So we're gonna use OT4. I'm gonna copy and paste this, and then do L, double check. It's called L. Okay, so the result will be OT3 and that OT3 like this. And then we can, because remember the issue of having separate mesh before is we didn't flatten it. So we need to make sure that we flatten this. So we change back to false here. What happened here? False. Let me see, something to do with the brackets. Guess we have 1. Okay, so now we have all sort of lines here, and because it's false, so it's gonna be an I list. So OT4 convert is going to be OT4 as I list object. Okay, and then we can create a temporary list line. This actually I'm gonna just ignore that. Code lines, new list. Because later on I'm gonna process this geometry through no encode, so I don't actually need to convert back to line or whatsoever. So I'm gonna keep it as an object. Just make this process easy. So lines dot add range. Just put in this OT4 OT4 C here, and then let's see what happens. Lines. Okay, here. So we get a bunch of lines, and if we try to change, maybe just go back here, then you probably notice so now we get lines following the iteration, which is great. But at the moment, you see at some point, we have basically sort of a separate clusters, right? And that is because we basically, if we start with, let's say, a rectangle with 4 points, then obviously everything will grow as 4 cluster, right? So in order to sort of connect them together, we have to do something to our point tree. So we have point tree somewhere here already, store all different generation. What I want to do is to put all the points into the same list and then find the average. So we're gonna get a center point, and then I can link everything to that center point. Okay, so here, what I want to do is I create a list called flatten, new list, because the point tree is, let me see, is point 3D. So I'm going to create list point 3D here. Okay, so to basically to put all the points in, we just need to run through each, let's say PA in PT tree dot path. So we run through everything, and then we, for each VAR call a random one PT maybe in PT tree branch. So you will see this process is very similar to what we just did here, right? So basically, we run through all the path, and then in each path, and then we get all the points in each branch. Okay, so now what I want to do, flatten dot add PT. So all the points will be stored here in one kind of flattened list. So inside one flattened list, then we can do something kind of interesting. We say average points equal new point 3D and flatten. Okay, that is a single list. So we say average. We're gonna do average, and then the point. So this is just an iterator. So point dot x. Okay, so all the point x value will be sort of average to one single number, and we do this with y and z, y and z here. Oops, here. Okay, so should be okay. Okay, so now we get one single point, and then we're gonna plug this single point back to. Let me just bring this back. So I'm gonna bring these points. Let me see which one has the PD tree. I'm gonna bring this point into the last branch. So everything when we search the closest point, you always link to that that point. Okay, so here we have this AV point, and then what we can do is to create a branch, a path. That's called new path equal gh path, and this time because remember what we did before, we always did -1 because of the number of iteration, but now if we just do number, so that is gonna be the last one. So number here, and then we can do pt tree dot add avpt and then new path. Okay, and once we do that, we can remove this -1. So then if we look at the network, that will always link to the center. Okay, so the average. Okay, so now what we need to do will be very straightforward. Then we just turn those lines into mesh, and then we do a reverb sort of Catmull clock algorithm to sort of smoothen it. Okay, so we get all the lines here. Then the next step is to use this. Okay, we need two methods as output 5 and 6, and it's called FT and WB. ft and wb here, and then what we need to put in here will be simply just lines, but we might see something kind of interesting we need to deal with later, and then gonna be just false. Okay, I'm gonna just grayed out this for now to see if it's working. op phi 0 here. So we're gonna get because the scale is so small. So in order to control that this component here, in order to control the radius, one thing here is you need to you can provide thickness. Another way you can have sort of a dynamic result is to provide basically a sphere. I don't know why you use sphere, but basically you provide sphere on each line so that you give a bit of kind of different thickness. So we're gonna create a list of sphere. Sphere new list sphere here, and then we do we need to count the number of lines we have, so we can simply just count the flatten or whatever. So this here we actually have not here. Let me just put in here. We iterate through all the points. Let me see here. What did we do here? All the lines here. So if I convert this into, let me see, maybe LL equal line. What is the objects? They are from, okay, actually I need to do this. I need to, okay, OT4 here, convert to Xi. Oh, I did that already here. So okay, so I have all the lines in this object. So what I need to do here is I'm going to do for each, run through all the. Actually, there are only one lines inside, but we still need to do this. L in OT for Xi. Oops. We're gonna run through each line and then convert that into a line, because what we want here is to get a sort of point that says at the start, and then create a sphere, new sphere. Here, maybe the radius can be 0.15, something like this. And then we're gonna put this into sphere collection, sphere dot add collection here. Let's see if we get that in. So now we can put the spheres here, hopefully. So now we get basically much thinner pipes. So the last one really is to basically do this silo, and then we can set the subdivision level, say maybe 2, just to make it a bit lighter. So now we get this kind of funny outcome. So if I go through this, gonna start with maybe 1, starting with 1 here. So this is based on the first generation with this random basic selection. So maybe the first generation, you don't see much difference because the number of points generated through this process are quite similar. But when you start like go to another generation, because the geometry that you sort of select will be different, then you kind of get quite dynamic outcome from this process. Okay. So that is basically what we want to do with the last exercise. And okay, now I'm gonna come back here. So basically, knowing code is very convenient. But any downside about this function? First of all, if you look at this process, so this is identical process. You do circle, divide, circle. Then you can see from output, you get the same thing. But performance-wise, obviously the script is still very fast because you basically don't have to handle a lot of unnecessary or additional information. That's why it's so difficult, because when you employ no encode and everything is sort of done behind the scene for you. So if you look at the performance, then it's actually a little bit slower. And then if you just pump the number of points up, then it's much slower. It's about like 4 times slower than just doing the script component. Maybe that's one reason. If you are sort of an advanced user, you don't do that, because then you know, it was just slowed down. But it's still quite an interesting function to use, especially when you deal with the component that is not available and you don't want to implement from scratch. So the last slide here, a quick summary about pros and cons. So just recap everything again. So no encode is very intuitive, very similar to components assembly principle in Grasshopper, and very easy to compose them together, very easy to assess plugin functionality, and it's very easy to do this kind of interoperability with another platform if the function exists. So some of the plugin allow you to access like additional sort of external software, so you can also implement that. And then it's able to access those components that is not documented in Rhino command. But there are a few constraints. So one is, if you see these kind of parameter, like internal parameters, you will not be able to do this. So what I mean is, if you want to, okay, doing flatten, this is simple, right? But you have something like reparameterize, then you always have to call additional function to do that, okay? And something like this bounding box, then you won't be able to just switch from one to another. So these kind of things that you cannot do. And some components are not supported, especially script-based component. So for instance, like Ladybug, that is a bit pity, because if you can run through all the iterations through this method, that would be much easier to use. And another thing is, this method is not suitable for external use. So you have, if you are in a big company and then you have a shared server with all the plugin installed, then that is okay, because you can always refer to the same plugin install. But if you need to exchange like components with people who don't have those plugins installed, and become problem. And lastly is the performance. So that is all about today. I hope that you enjoy. I'm kind of like just squeeze everything into this like 2 hours ish time, a little bit fast. So